Right. So while we're waiting, do we have any questions from classes so far? Any other topics? Open up 3 minutes. Any doubts, any questions that we must discuss? We are also completely have no questions. There this time, let's get. So this really happens. The very first time I taught this course, and the very first lecture that I did, was a big kid office at Alpha. Somebody's coming up. Came to my office after class and he said, I have no question because I'm Christian. So it was a very profound statement somebody made. And that's my entry point into CMU, my teaching career, and also very, how should I say, humbling. So I don't expect at any moment that anybody has understood anything I have taught in class. I do try very hard to make sure that I'm understood, but I don't think I always succeed. Which means that if you guys haven't understood something, if you have no questions, the fault is mine. If you haven't understood something, it's probably why you're in class. So it's my job to make sure that you get it right. I can't hear you, so can you speak up?
Sorry. I have a general question about the math part. So like how much of the math part should be like?
So the math, I just, you don't do a lot of math in this process, have it observed, right? Pretty much the only concept that you have to look into is student presence. But what we are trying to convey over here is that we can go pretty far in a rigorous way without very little amount of math. And if you haven't been convinced of that yet, it should be right. Pretty much everything that we're going to be doing is going to be looking at inner products and pseudo inverses and matrix inverses, except for the little bit where we are talking about statistical estimation and so on. So yeah, it's useful to get into the math because it's nice to know, where these things come from. But the fact of the matter is that once you get a hang of basic concepts, then the math is just slave, it's not your master, right? And so you can, so long as you know what thing does and what can work at that level without getting into the weeds, which should be fun. No, if you're writing rigorous papers for the IPP transactions, okay, if there are a lot of machine learning research, you have to put some theorem, but you do have it. Okay, it's 2:06, so I suppose that it's going to take a couple more minutes for Master to come. Oh, yeah, I was waiting for you. Okay. So, see, it's positive feedback. If you take them back, take them off, you can't see them. If you can't see them, you can't find. On? Perfect. Can you clip it on? Thank you, Masa. Where does it? Yeah. Okay, guys, can you hear me? And David, am I audible on the on Zoom? Okay, let us begin. And here we are. So we're going to be talking about supervised representations. Now, the last 2 classes on expectation maximization were a bit off, off the trajectory, off the storyline that we had, primarily because we had Tuesday off this week, and so we had a break. And so we had this 1 lecture slot for the week, and I had to reshuffle things. Otherwise, this is what I would have done prior to EM. We would have had a week of EM, and then I would have talked about factor analysis and so on. And somewhere in between, I would have also tried to fit in a lecture on time series analysis. So I'm going to have to figure out how to shuffle this. You can thank Donald Trump and Kamala Harris for this. And now, yeah, we're talking about supervised representations. We saw very early in the class that one of the big, machine learning can be applied at all points of the signal processing chain. And one point where we applied it a whole lot wasn't feature extraction. How do you extract features from data? And so we saw the very first thing we saw was some basic mechanisms for extracting features where we basically viewed projections or explanations of the data in terms of bases, where the bases were data agnostic. You just came up with the bases without really considering what the data were being used for. So we were using things like square waves, sine waves, complex exponentials. It has nothing to do with the data. Then we made our first improvement where we figured that the bases that we use to explain the data must depend on the data itself. And so there we saw principal component analysis, independent component analysis, non-negative matrix factorization. All of these were different mechanisms for deriving bases from the data, but each of them had a specific objective. They tried to explain the data in a particular manner with the assumption that if you applied the right constraints, then the basic building blocks that came out would make the most sense, either in a generic construction, from a generic construction perspective, or more from a more specific perspective of, there's something that you want to do. But then the second aspect, if there's something that you want to do, must really consider what you want to do, right? Whereas I said, we came up with some mechanism for explaining the data, hoping that our explanations would allow us to do something with these explanations. So NMF, for example, we said, if I impose not constructivity as a constraint, I'm going to get a bunch of bases. And then when I use those bases, I found I could separate signals out, I could complete signals and so on. But during that process of designing the bases themselves, I never took into consideration the fact that I would be using that decomposition for the specific purpose of separating signals or reconstructing damaged signals. The actual task that I was performing was not considered. Our basis decomposition was done in an isolated manner without considering the task. So what if we also consider the task itself when we design our bases, when we derive our representations? That's what we're going to be looking at today. So we can have a couple of different tasks. Things can get more complex than this, but we're going to look at two specific things: linear regression and classification, linear classification. Now we can expand out from these two tasks into other tasks, and the models get more complicated. The idea here is that we want to present a specific perspective for how we can derive task-specific bases. So think of linear regression. Here we have some variable y, which we would like to predict using some variable x. That's what linear regression was, right? So now, when we did it naively, we just tried to predict y from x. But then does every aspect of x relate to y? Most likely not. And so can I find a basis decomposition for the data x that is most appropriate? In the standard data-driven representation, if we were just using the standard mechanisms, if I was trying to predict y from x, I would find some basis representation for x, use that to represent x, maybe perform PCA on x. I'd find some standard basis representation for y, maybe perform PCA on y, and then try to predict y from the PCA basis-based representations of y from the PCA basis-based representations of x. So both of these we're deriving representations for both sets, x and y, without considering each other. Can I do this better if in the process of representing y, I also consider that this representation of y must be predicted from x? In the process of representing x, I also take into consideration that this representation of x must be used to predict y. So we have task-dependent representations of the data. Similarly, if I'm performing classification, I get some features x, and I want to decide, is this a dog or a cat? Is this class 1 or class 0? So in this case, now, if you're doing a standard database, data-driven representations, you just perform the PCA on your data.
use those representations and build your classifier. The task of the fact that the task you're going to be performing is classification is not being considered in this step. If I actually factor this in and consider the task itself when I derive my representations, and I do better. So this is what we will look at, both of these, right? Now, in both of these cases, what we are really looking at is task-dependent derivation of representation. So once you make these things task-dependent, the task is essentially a supervision. It tells you, here's what you're supposed to be doing with this representation. So these are supervised representations. And so when I come up with a basis decomposition for the data, we are going to be looking at trying to find bases that perform these tasks best using our supervision. So the bases that would give us the best classification performance if the downstream task is classification, or the bases that give us the best regression performance if the downstream task is regression. So that when we represent the data in terms of these bases, you can perform the regression or classification better. In general, you think of these two, the task is one view of your data, and the actual input feature is another view of the data. You can think of this as X and Y. Y is something you're predicting. It could be a class, it could be a feature. X is the data that comes in, again, something that you're using to make the prediction. But then from our perspective, these are two different views of the same world. You're just looking at it from different angles. And so you're trying to generate views that support one another. So to give you a better example for how we would do this, I'm going to start with linear regression. And when we use this for linear regression, we end up with what is called canonical correlation analysis. I think that Chuck's here. So yeah, consider this example, right? It's a very hokey example. You're trying to make predictions. And say you're an archer. How many of you have actually gone down Fifth Avenue on Saturday or Sunday, right? If you go to the end of Washington Boulevard, there you got to find a bunch of people every weekend. They set up this big archery board, and they come out with their bows and arrows, and they shoot up the poor board. And often they miss the board and they shoot up the forest behind it. So, and then they have other guys dressed in medieval armor fighting each other, stuff like that. So, say you're one of these guys, right? And so you're going to have a target of this kind, a bunch of circles. And so your task is going to be to hit bullseye. But then you shoot the arrow, and let's say you're a fantastic archer. In the absence of wind and other distractions, you would hit bullseye every single time, okay? But then there's wind. What happens when there's wind? What would happen? Why? The wind is going to move the arrow, right? So you're going to have, you're shooting the arrow. There's a crosswind. The arrow presents a face to the wind, and it's going to push the arrow, right? How much is it going to push the arrow back? How much is it going to make your, if this is X, and this is Y, how much is it going to make it shift by? How much are you going to miss by? Pardon me? It depends on the wind. It depends on the wind velocity and a couple of other factors like how much, what is the cross section of your arrow? How much of it is actually, how much force it actually imposes on the arrow? What acceleration or velocity it affects on it? What is the distance to your target? Eventually, your arrow is going to end up somewhere else, which has an X shift and a Y shift, right? And so that is going to depend on the velocity of the wind. The faster the wind is, the more you expect it to drift, right? And so if I had a wind sensor, I lick my finger, I stick it out, I can feel the wind on it. And they actually do this. And then, they shoot based on what they think the wind is. And that's how they make their corrections. So I measure the wind speed in 3 directions, along X, along Y, along Z, right? And so the wind speed I can write as a vector with 3 components, the x, y, and z component. I have the extra 1 because when at any time I do a linear regression, what is that 1 doing over here? Yeah, it's the bias, correct? We stick an extra 1 to account for the bias. And so the amount by which this guy shifts is going to be proportional to the wind velocity. The larger the wind velocity, velocity times time, right? And so, and times some function, which is the cross section of the arrow. And so you would expect some function of time. Actually, let's just call it sub alpha times whatever time it takes for the arrow to get to the target. And this again is going to depend on how much it drifts. So some crazy function, I'll just call it alpha times wx is going to give you some idea of how much it shifts along x, right? And but is this all? That's not really what it is, because there's a coordinate system, there are things happening. More generally, I can think of my drift as a vector yx, y. I'm just reusing this x and y, unfortunately. And so, is that right? Or let me call this ox and oy, which is going to be, so if this is 0, 0, the coordinate over here is ox, oy. And this is how much the arrow has drifted by. And that's going to be a function of the wind velocity, right? And so this is going to be some wind velocity vector. I'll call this x for now. And it's going to be linearly dependent on the velocity, right? So if it's linearly dependent, there is some, for each component, there's something over here. So let me call this matrix beta transpose. I'm calling it beta transpose because the x component depends on one row, the y component depends on the other row. So I've just put in a transpose there to make it more appropriate, right? So each beta itself will have as many components as the wind. And so I can just write that the offset is going to be some beta transpose times x. Is this making sense? Right? The larger the wind velocity, the more it's going to be offset, or at least it's going to be linearly dependent on the wind velocity. That's the expectation. And so what does your life experience tell you? Every time you go down to the end of Washington Boulevard and lick your finger and stick it up, how has that helped you shoot? What does your life experience tell you? Yeah.
Kind of being in the opposite direction of the wind.
Correct, but you're learning the beta, right? So you're going to go out there, you're going to be shooting lots and lots of arrows, and you're going to be missing wildly all the time, even though you're a perfect archer. And so each time you shoot, you have an x, which you obtain by licking your finger. And then you get the y, which is how much you figure out what the offset is. And so then you determine the characteristics of the place. You can just say, yi equals beta transpose times xi for each of your attempts at shooting. So if you have a large collection of these guys, this is your life experience all the way until now. And so you have a collection of y's, which I can say y equals y1 through yn. These are your n training instances. X equals x1 through xn. So again, these are the wind velocities in each of your training tries. These are the offsets in each of your training tries. And then, so what is the relationship between y and x over here? Anybody? The way I defined it, what was it? Come on, guys. I gave this here, right? Same thing. It's an affine relationship. Correct. So I would write y equals beta transpose times x. I factored in the bias because there's a 1 in the x. This is the relationship you have, correct? Everybody agree with me on this? And what is beta now? So now you're at the competition. What do you really want to do?
Beta.
You want to find beta so that you can correct for it, correct? What is beta? Yeah, but how do you derive beta? After a semester of MLSP, you should be able to tell me what beta is, right? Everybody agree that it's, what is beta? Yeah, so beta transpose is going to be what? Somebody give me the answer, please. This is going to be y pseudo inverse of x. Correct? Or alternately, I can write beta equals P inverse of x transpose y transpose. Does this make sense to you guys? Everybody remember, I know I've been away for a month, but you couldn't have forgotten. Okay? Yes, okay. And this was easy. This we know, right? And so that's what we have. And that's the formula for the pseudo inverse of x and y, okay? Now, what exactly are we doing? Even if we go there, before I go there is the, okay. So if I have this, is everybody with me so far? Okay. And in this setting, again, I just ask you to recall from memory that the pseudo inverse, so x after many tries was longer than it was tall, right? So would x be, so is x transpose going to be invertible, or is x transpose x going to be invertible? Which of these two is going to be invertible? X is wider than it's tall. Come on, guys. X transpose is going to be invertible, right? And so the way we set up, we always go with the one that's invertible, right? So if I was going to be writing as y equals, let me just call this beta transpose x, I can multiply by x transpose on both sides. This is invertible, correct? And so I can write beta transpose equals y times x transpose times x transpose inverse. Everybody remember this, right? And this, what was this term here? What was that? That was the pseudo inverse, right? And so I can because I'm writing beta transpose, I can transpose the whole thing, and that beta becomes x transpose inverse times x times y transpose. Everybody with me so far, okay? And so I have come up with a beta. So and I have said y equals beta transpose x, where beta is given by this formula here. And now, what is this kind of a formula over here? This, what does beta transpose really represent for x of the relationship between x and y? The set of weights, but what are those weights conceptually? This relates to the correlation between vectors, between random variables. How do you understand correlation? Suppose I told you that the correlation of x and, I won't call this x, correlation of, say, give me two variables which are not x, y, u, v, or w. A, b, thank you, right? If I say the correlation of a and b is 1, what does this mean? So I'm speaking of the normalized correlation where a and b are locally unit variables. What does this mean? Highly correlated. What do you mean by highly correlated? What do you mean by highly correlated? Anybody? The change of one variable is going to lead to the change of the other variable. By how much? The same amount. So this tells you how much B tracks A. Right. So if A equals A1, it tells you that the expected value of B is probably going to be A1 as well, because they're going to be tracking each other perfectly. That makes sense? That's what the correlation was. And so suppose this was 0.5. What does this tell you?
8 racks half.
8 racks half B, right? So this it actually gives you at a very crude level, you can actually see how this works. Again, I don't want you to get married to this particular visualization, but you can think about it roughly so. This is x equals y, where everything x and y are going to track each other perfectly, correct? Whereas if the correlation is 0.5, then as x increases, y increases by 0.5. But then as y increases, x increases 0.5, right? And so you're saying that there's that much more uncertainty between the in the relation in x every time you see y and vice versa, because those are the two lines within which the data roughly fall, right? So you're getting you get some kind of an idea of how this works. And when it's 0, it means that it can be anywhere. The whole thing is, as the number increases, then this becomes your entire, as the number decreases, when the correlation is 0, then as x increases, y stays 0. As y increases, x stays 0. Basically, it means that the entire data the uncertainty is the entire circle, quadrant, right? You can also change the angles. For -1, it's so you get an idea of how the whole notion of correlation works. The correlation basically tells you how the two variables track one another, okay? And so when I say y equals beta transpose x, what am I really telling you? Beta is some kind of a correlation between x and y. Beta is how much y tracks x bar. That makes sense to everybody? Okay. And so when I say y equals beta transpose x, what is this an equation for? Geometrically. It is a hyperplane, right? And so basically you're saying that your best guess, if this is x, in 2 dimensions, it would be a line. In 3 dimensions, it's probably going to be some kind of a hyperplane. At any given x, xy location, my best guess for y, in the absence of other information, is a point on this hyperplane, corresponding point on this hyperplane. And the gradient of the hyperplane is basically giving you the correlation between y and every component of x. That makes sense? So, is everybody with me? Okay, so now this is where things get more interesting. So any questions so far about the guys at the end of Washington Boulevard? None. Okay. Now here's the thing. I have my target, and Vidur there shooting arrows at it, bullseye. And now there's a wind. Now the arrows is a flat object. It's got an x surface, a y surface, but it's impossibly thin. That's where it's a hypothetically perfect arrow, which means that if there's a wind in the direction of the target, is that going to change the how much it misses by? Not at all, because there is no cross section, right? But there are cross sections in the other 2 directions. And so now let's say my wind is traveling this way, blowing in this direction. It's got an excess, it's got all 3 components. Is every component of the wind going to affect my target? What components are going to affect the position? The x and the y, right? So if my wind is going off and doing something crazy, so far away there's my target, and here's my archer standing with his arrow. And if the wind is blowing in this direction, which has got x, y, and z components, then how do I find out what components of the wind actually will affect the position? Right. So this is my target, right? and the wind is blowing in this direction, or maybe in this direction. So what do I need to do to find out how much of the wind actually affects my arrow? Projection, right? Because I know that any component of the wind in this direction is not going to affect my arrow. So I take this wind vector over there and I project it on my XY plane. And whatever aspect of the wind vector is on the XY plane is the only component that's going to be affecting my arrow position. Does that make sense? Right. So what is this business of projection? It's multiplication by matrix. Right. And so not all components of the wind are going to be affecting my arrow position. There's some matrix U, my projection matrix, which projects it onto the appropriate surface, onto the appropriate subspace, where all the relevant components lie. And so I can think of this as X hat. I've got transposes all over here because these are standard notations that I drew. Maybe I should get rid of them, but live with them, right? So U transpose is the projection matrix. U has as many components as X. That's why I'm doing the transpose. And the U transpose X is the projection of X, which gives me all the meaningful components of X. Right? Does that make sense to everybody? But then there's the other thing, right? There's a wind, and let's say I'm shooting arrows. When I'm shooting arrows, there's some inherent noise in the process itself. Maybe my hand tends to wiggle. I'm not accurate, so my hand tends to wiggle in the X direction a little bit, not very much in the Y direction, okay? So if I'm shooting perfectly straight, even so, I find that I don't actually hit the bullseye. I get some scatter, which is spread more along the X direction in the horizontal direction and less in the vertical direction, okay? So if that is the case, and these things get exaggerated by my wind, let's just assume, right? So in the absence of, so the actual wind causes the scatter due to the nature of the process, which looks like this. But then when I fix my bullseye, I'm measuring the coordinates, correct? How much the offset is by. And then for whatever bizarre reason, is there a colored chalk? Apparently not. Open it. Okay, I have fat chalk. A little bit fat chalk. Okay. So for whatever bizarre reason, I use these as my axes, coordinate axes. So this is not X, this is not Y, this is X and this is Y, but my scatter is horizontal or vertical. Okay, when I do this, right, what am I going to find? Anytime I find a small shift in this direction, am I going to find a shift in this direction as well? Considering that my scatter is actually like this. Yes or no? Right, because my scatter's primary direction is here, right? If there's a movement in this direction, if I've got some point here, if it's got a movement in this direction, then it's also got a movement in this direction, correct? So, which means that my two coordinates are correlated, they're related. One of them is telling me something about the other. Whereas if I were using these guys as my axes, would they be correlated? So if I use the appropriate coordinate axes, I could be making predictions about the shift along X and the shift along Y independently of one another. Whereas if I'm using some other inappropriate set of axes, then they're all going to be married to one another, right? So what do I want to do? I want to be able to make predictions independently in each direction, right? What must I do?
Correlate your axes.
How would I decorrelate it?
Solid ICA. Or
I can do this. I can just shoot lots of arrows. I can look at my scatter, and then I can actually set up my bases along the directions of the scatter, and they're decorrelated, right? So in other words, I'm going to be the actual, so I can think of this as some, this can be even a low dimensionality reducing projection, right? Maybe I just always miss only along the horizontal axis, right? So the wind is going to have an influence, not influence every aspect of my arrow position. It's going to be influencing some lower dimensional projection of my arrow position, right? And so here's what I have. Did all of that make sense? So there's some lower dimensional characterization U transpose X of the wind, which influences some lower dimensional component V transpose Y of the arrow position, right? And so now, if I'm trying to find a relationship, should I be finding the relationship between X and Y, or should I be finding the relationship between U transpose X and V transpose Y? Which ones? Because I should be finding the relationship between the aspects of the wind that actually influence position and the aspects of the position that are actually influenced by the wind. The rest of them are irrelevant. That make sense to everybody? Yeah.
When you're considering the second set of coordinate axis is there, is it because of the wind?
No, your coordinate axis can be anything, right? So you want to sort of shift it so that
You can go there.
you can make the predictions independently, right? I mean, I could be even, it could be a dimensionality reducing projection. Maybe you always, think of it this way. Let's say you go ahead and use the standard bases, but then you always miss only in this direction. Then does it make sense to be trying to make two predictions? It makes, instead you want to use this guy as your basis, and then you're going to make only one prediction, right? It makes sense? And so that's what you want to do. And so we want to find a projection of the wind vector X and a projection of the arrow location Y such that the projection of X best predicts the projection of Y. In other words, you want to find the projection of X and the projection of Y that are most correlated. That makes sense? Right. So this is classical, this is canonical correlation analysis. And what do these projections represent? They actually represent the direction of max correlations between these two. And this ignores the parts of the wind and the location data that do not that are not influenced by one another. Only the information about the defective arrow which keeps moving around remains, right? And the specific positions, the specific errors that they cause. So what is my job? This is a very trivial example, arrows and people shooting at stuff. But in real life, it gets a lot more complex. The data can have any number of dimensions. It's not immediately apparent which components of the observation X and which component of the predicted variable Y are related to one another. So in other words, our job now is to actually determine the matrix U and the matrix V such that I get the most useful aspects of X and the most predictable aspects of Y. And then I can relate the two to one another. That make sense to everybody? Okay. And so I'm going to skip a lot of this, the math on my slides, because who wants math? You just want to get the idea, right? You agree? So now, what would be the easiest way of doing it? I can just say, I'm going to take my X's, I'm going to take my Y's, I'm going to perform PCA on them jointly, and maybe I get something useful. But will that work? It won't work because for two reasons. First, if I just take my X and my Y and I perform PCA on it, it's going to mix up the X and Y. You're not going to be able to separate out the input from the predicted variable, number one. Number two, PCA is going to decorrelate the whole damn thing. What we want to do is to decorrelate X, we want to decorrelate Y, but we want to maximize the correlation between X and Y. You want X to predict Y, right? So you can't just use PCA over here. You have to do something smarter. And so what is it smarter that we will do? First, I'm going to define some variables that you're all very familiar with, correlations. So again, what are correlations? Correlations tell you how much variables track one another, right? And we are familiar with correlation matrices. If I've got a vector X with many components, then what does the correlation matrix look like? It's square, correct? And this is going to be x11, x12, and so on. This one tells you how much one tracks itself. So it's just going to be the variance of x1. This one tells you how much one tracks two. This one tells you how much two tracks one. They're the same thing, right? And so the correlation, and these are statistical correlations. They're tracking. But if you want to derive this from data, you're just going to take lots of x vectors, multiply them by their own transposes, and take the average. So this 1 over n xx transpose is your estimate for the correlation of an x vector with itself. That makes sense? Right. Similarly, I can get a correlation vector for y. Then I can get a cross correlation between x and y, which is, this is going to be if I have an x and I have a y. And if I have a y, which is some number of components, then the cross correlation between x and y is going to have, cx1, y1, cx1, y2, and so on. Right? And so this tells me how much y1 tracks x1. This one tells me how much y2 tracks x1, and so on. Each of them is tracking. You're looking at them independently, but they actually, when you actually do the math, you have to consider them jointly. Okay, does that make sense to everybody? That makes sense, okay? And so your correlation matrices are just 1 over n xy transpose. These are the estimates. You would have to do this with over tons of data to get the actual statistical correlation matrices. And so now the cross correlation between x and y is this guy here. The expected value of xy transpose, this is what we just saw. And now here's the thing. If I project x down and I project y down, then the cross correlation is going to be between x hat and y hat, which is the expectation of u transpose x and v transpose y. Right? So if I take x hat times y hat transpose, I just plug this in. X hat is simply u transpose x. Let me write this down. So, okay, is everybody with me so far? Right? So, and you see what I'm trying to do here. So I have taken x and I've converted it to u transpose x. I've taken y and I've converted it to v transpose y. I want to find the cross correlation between these two guys, which is going to be u transpose x. What is the transpose of this one? Y transpose v. But this is the expectation, which is simply going to be the u times the expectation of xy transpose times v, sorry, u transpose, right? And this is just the cross correlation between x and y. And so that's simply going to give you u transpose cxyv. Or if I'm trying to derive this as an estimate from data, that's simply going to be 1 over n u transpose xy transpose v. So everybody with me so far? Okay.
So if you say that, are we like normalizing the x and y values?
We have not done anything so far. We have not done anything so far. Okay. But there's something magic happens in the pseudo inverse. It actually automatically gets normalized. But you'll see how this works over here. We're going to see how the normalization comes out because it has to be scaling invariant. It's a very nice point. Let's see how this works, right? So here's what I want to do. I want to maximize the cross correlation between the projected x and the projected y. That makes sense? Which means I want to maximize this guy. Now this CXY I can estimate from my training data. I've gone to this a course at the end of Washington Boulevard for several weeks. I've shot 1,000 arrows. I can compute CXY, right? And but then I want to estimate U and V such that this guy is maximized. Can I just do it blindly? Yeah.
You have to make sure that X and Y individually are correlated, right?
Yeah, but there's something more about
I just maximize it. Can I not just multiply U by 1,000 and increase it? This guy, if I do this here, I can just scale X, I can scale U, and I can scale V, oh, sorry.
and the number will increase, correct? That makes sense? So can I just blindly maximize this guy without additional constraints? So what constraint must I have?
The size of
U and V should have the same, they should retain the length in some sense, right? U and V should not scale. If U and V do not scale, what does it tell me about U and V? Their eigenvalues are all one, right? They must be rotation matrices of some kind. Otherwise, they're just going to be scaling things. Okay. Now, there is another way of increasing this guy. Instead of reporting everything in centimeters, I can report everything in millimeters. Is that useful? Right? Instead of saying it's missed by 10 centimeters, I say I missed by 1,000 millimeters, 100 millimeters. Have I improved the cross correlation? No, right? I can say I have increased. This is actually 1 million watt nanometers. Has that actually changed anything in life? No. So how do I account for that? How did we account for this earlier? We whitened it, right? We normalized it. We wanted to make sure that, regardless of the unit you used, when you look at it, everything eventually became the same thing, right? So statistical whitening. And so how do we constrain this? We can scale up U or V or X or Y. We don't want to do either. And so we're going to whiten X. We are going to whiten Y, and we're going to be making U an orthonormal matrix. Why is it an orthonormal matrix? Orthonormal matrices, the eigenvalues are all one. They're never going to increase the length of a vector. That makes sense to everybody? Okay, that makes sense to you, and to you, and to you. Yeah, okay, all right. Questions? That's a lot of things to be doing all at once, correct? I have a whole bunch of constraints. Can I compact them all into a single constraint? Or two?
Lagrangian multipliers.
Lagrangian multipliers, but here's what we're going to do first, right? Again, this is just the point is that the covariance of U transpose X is simply U transpose covariance of X times U. This is, we're just going to be using this math. Okay, this one, do I need to go over this? This is easy, right? And so here's what I'm going to say. I'm going to say, I want to maximize U transpose CXV, but then I have all of these other constraints. U and V must not increase the length of vectors, and X must be unit invariant, correct? So in other words, I want to make sure that whatever U is, whitens X. Whatever V is, whitens Y. Okay? So is this making sense to you guys? I've factored everything in. Now, when we were whitening things, what did we use to whiten a data? How did we whiten X? Anybody remember? How did we whiten X? Come on, guys.
First, we center the data.
Mm-hmm. Okay, assume everything is centered. Okay, then how did you whiten it? Can you say that aloud, please? The inverse of the correlation matrix? You're getting close. How did we whiten data, right? You had X. You wanted to have some A times X such that the expected value of AX, X transpose, A transpose was the identity matrix. That's what whitening did, correct? And so we said that our whitening matrix was the covariance matrix raised to minus half. Anybody remember this? If you divide by the standard deviation, the variance becomes 1. In the matrix world, what happens? What is the division by the standard deviation? Multiplication by the square root, division by the square root of the covariance matrix, right? The standard deviation is the root of the variance. In the vector world, the corresponding is c raised to minus half. Do you guys remember this? Yes or no? Can I hear a loud yes?
Yes.
Okay, she's lying. But what about the rest of you guys? So, is that the only matrix that whitens?
Should be able to rotate any.
So here is what happens, right? Here, that's perfect, Ajay. So here, if I have a scatter that looks like this, then if you multiply this data by c raised to minus half, if you multiply this data by c raised to minus half, this scatter is going to become like so, a perfect circle or a perfect sphere, right? But then if I multiply that data by any rotation matrix R, will the scatter change shape? It's still going to be circle, right? So any matrix that has the form R times c raised to minus half, where R is a rotation matrix, is going to whiten. There's an infinite number of whitening matrices. C raised to minus half is just one of those. And so we're going to have to search from amongst the entire set of possible whitening matrices. That makes sense to everybody? Okay. So, but then on top, we're saying I'm going to maximize a matrix. What do I mean by maximizing a matrix? What am I really trying to do? I'm going to be maximizing the correlation. So what should I really be maximizing? The eigenvalues of this guy, correct? You want to maximize the eigenvalues of this matrix. In other words, so what I can say, or I can say I want to maximize the sum of the eigenvalues. And what is this? What is maximizing the sum of the eigenvalues? What is the sum of the eigenvalues of a square matrix? It's the sum of all the diagonals, right? It's a trace. And so what we will do is simply say we're going to be maximizing the trace of this matrix, which is the sum of all of the diagonal elements subject to these two constraints, okay? And why the trace? It turns out that, stretching, rotating, and transforming the space in any way, and then computing the trace and then unstretching it will not change the trace. So these are called similarity transforms. The trace is unaffected by pre and post transformations. The trace of B is the same as the trace of A inverse BA. So which is why we use the trace. It's robust to transformations, okay? We have our first pole. I'm actually only a quarter way through the lecture, so I'm going to jump. I've gotten unused to teaching in the classroom. Over Zoom, it's so easy. I just pretend I'm there. You pretend you're there. By the way, did all of this make sense? We'll skip the math, okay? Who wants the math, the derivations? In class? That's okay. Okay, I'll skip it. I don't have time for it, but it's on the slides. Yeah. Okay, anybody want to answer that first question? True or false? First statement. Second one. Are PC and NMF true or false? Third one. Can I just concatenate X and Y and run PCA on it? No, so true or false? And the fourth one? And the fifth? True, right? So this is why we chose these. Everybody good with me so far, right? Okay. All right. Now, where some history, right? So this is basically what we want to do. This is the canonical correlation analysis. Why am I maximizing the sum of the eigenvalues and not the product? Anyone? Why did I choose the trace and not something else? In fact, the product of the eigenvalues is actually a nicer thing in some sense. Because if you choose one dimension too many, there might be some dimension where the total variation is 0. In which case the eigenvalue along that direction is going to be 0. If one of the eigenvalues becomes 0, the product stays 0. It doesn't matter what you do with the rest of the guys. So the product is a horrible thing to optimize. We optimize the sum, and so we optimize the trace. Okay, make sense? Okay. So this is canonical correlation analysis. It models these two variables y and x as different view of a common reality. You say the two views are correlated, and the challenge here, and you say each view is locally perturbed by noise, and the challenge is to extract the correlated subspaces of x and y from their noise. So here's a standard picture. X's that the data lives in is a combination of x and y. It lives in joint xy space, right? And some joint space. And your features x are one projection along one plane. And the predicted variables y are some other projection along another shadow along another plane. And from these two shadows, we're trying to reconstruct the real world, which are the balls, except the shadows are going to be corrupted by noise. And we have to learn to ignore the noise, keep what is relevant so that we can construct our view of the world. And so this is why it's called a multi-view assumption, that there's a source which is generating both of these views. Each of these views is independently corrupted by noise. What is common is the source. So the probability distribution of view 2, given the source, is independent of view 1. But if I don't give you the source, the probability distribution of view 2 depends on view 1. And so we're trying to maximize the, we're sort of trying to eliminate all of the correlations that don't really reflect information about the common source in this process. So some examples. I could be looking at stocks from many different sectors of the economy. And so the stocks from different sectors of the economy are going to have very different behaviors, right? But are they unrelated? They are not. Are they directly related? No. I mean, how does the price of cabbage relate to the price of Apple shares? It doesn't, right? Not directly. Or does it? Is there a relation at all? There is. If the economy stinks, cabbages are expensive and Apple stocks nobody cares for, right? So there's an underlying economy that really affects both. But if you're not looking at the underlying economy, then you'll be perfectly, valid in assuming that you can look at the prices of cabbages in the market and predict the price of NVIDIA, right? So because they're all reflections with different levels of noise of an underlying economy. So this is where the economists came up from on the whole idea of canonical correlation analysis. You're assuming linear models, so you can extend this to nonlinear models. Or in speech, you can have multiple speakers saying the same sentence. If I know what the sentence is, then my recording and her recording don't have any relation to one another. But if I don't, they're related, right? So how do you extract what's common? There's some math over here. Do you want me to go through the math? I'll quickly tell you what the math is. What we're really trying to do is trying to find a projection of x and a projection of y which predict one another. In the ideal world, the projection of x and the projection of y are the same. So I'm minimizing the error between vx and uy. And that's just the Frobenius norm. Subject to these constraints, I want each of them to be individually weighted. So when I work through the math, if I have constraints, how do I apply the constraints? I just apply them as Lagrangians, right? So this is my trace. The Frobenius norm is a trace. I'm not going through the math again. To this trace, I'm going to add, I've expanded it. So you want to maximize the trace of your transpose CX by the subject to the constraints and Those I can add as Lagrangians. And when I work through all of the arithmetic, I end up with these very nice closed form solutions, which says that the Lagrangian parameters for x and y must be the same, they're common. And I get this a system of equations which are really very trivial, where cyx and cx and cxx and cyy are all easily estimated from the data. Skip the math, there's a nice closed form solution. You can work through this on your own, and in paper, it's not too complicated, right? The point is, this guy here, what does this equation look like at the bottom? B is a diagonal matrix. What does this look like? Anybody? I'm saying C times V, there's this ugly matrix here. Okay, there's this ugly matrix here that's multiplying V is the same as multiplying V by V squared. What does that look like? It's an eigenvalue equation, is it not? It's just a very ugly looking, but very straightforward eigenvalue equation, correct? So what is this first term over here? This is like saying, I'm going to use Y to predict X. Remember, the correlation between X and Y is telling you how Y tracks X, correct? So I'm using Y to predict X. Then I'm whitening that X by normalizing. Then using that X to go back and predict Y. And then I'm whitening the Y. Right? And now I'm looking at the correlation between these two, predicted and the originals, predicted Y and the original Y. That's giving me a correlation matrix. The eigenvectors of that guy are going to give me my V, right? In the other case, I'm going from, here I went from Y to X and back to Y, right? So if I use Y to predict X, use the X to predict Y all over again. If it came back exactly the same, X exactly perfectly tracks Y. If it doesn't, there's some noise, right? So I can look at the correlation between the two, that correlation matrix. The eigenvalue vectors of that correlation matrix gives me V. Here, I go from X to Y and back to X. And the eigenvalues of that correlation matrix gives me V. Very simple. I mean, if you look at the equations, everything just makes sense. That makes sense to you guys? She's looking lost. That makes sense. Okay, so you know, we saw what the correlation was. When I say Y equals AX, right? A tells me how Y tracks X, correct? So CXY was told you how much you had to multiply Y by to predict X, correct? So I went from Y to X. But then X is not normalized, so I normalized it out to get rid of unit dependence. Then I use that resulting X to go back and predict Y. But then I normalized it out to get rid of unit dependence. And so I have the initial Y and the predicted Y without unit dependence. I look at the correlation between the two. The eigenvectors of that give me V. I do the same thing for X. The eigenvectors of that give me U. Okay. So, all right. So we just have to find the eigenvectors of this guy, right? In PCA, the eigenvalues were the variances of the PCA bases, right? You just look the correlation matrix and computed the performed eigen decomposition. Here, you're performing the eigen decomposition of what is called the canonical correlation matrix. That's the canonical correlation matrix. And the directions that you get are the canonical correlation directions. Okay. So some more math, I'll skip it, right? In fact, I'll skip this because I don't have time. So where did this come from? This actually goes back, canonical correlation matrix goes back to this guy called Hoteling in 1936, who realized that in many real world problems, you're actually looking at two views of the data. So for example, if you're worried about wheat, right? Wheat is expensive, so but you need wheat to make bread. You decide, okay, this thing's too expensive, so I'll buy something else. But then if you buy something else, you're consuming that something else as well, right? So how much is the consumption of wheat dependent on? What is the consumption of wheat dependent on? Is the consumption of wheat dependent only on the price of wheat? What else would it be dependent on?
price of the other foods.
The price of the other things. If potatoes are expensive, more expensive than wheat, you're probably going to prefer wheat, right? You're not looking at anything in isolation. And so you have these two views. How many potatoes do I consume? How much wheat do I consume? How much rice do I consume? So the consumption vector of many variables and the price vector of many variables, right? These two are related. They're not independently related. They are jointly related. But then are they just perfectly related? No, there's noise, right? You have other factors. Maybe the wheat didn't grow. Maybe some guy is hoarding money. Maybe the rats ate the wheat, right? So you have these. So you have some down projection of the consumption vector that's predicted by some down projection of the price vector. And what are these down projections? And what are the corresponding directions represented? That's basically what we just saw. That is the canonical correlation analysis. And that's how the math was derived, right? Very beautiful. And you can apply this all over the place. You can apply this to the stock market. You can apply this to predicting stocks tomorrow, to predicting all kinds of things. And these guys, Magnus Borga and David Hardoon, showed that you can apply for signals. So here, for example, if I've got data from two classes, red and blue, if I just throw them all together and perform PCA, I'm going to get the two pink lines as my bases. But if I perform CCA, the matrix for U and V are not relating to one another, right? U and V are, so there's no requirement that U must be orthogonal to V. And so U and V can actually have some angle. And so the two CCA bases are going to be these two green bases over here. Now, how are they different? So if I actually look at this, yeah, this is PCA. If I look at the two PCA bases and look at the projections of this data on the two PCA bases, can you separate the red from the blue? They're all over the place. Each of the bases has both red and blue mixed into it, correct? Whereas if I use CCA, you find that in each of the two bases, the red and the blue separate out nicely, right? So by having this additional supervision that there are two classes over here, CCA actually gives you a much nicer representation of the data, which allows you to make these predictions. Okay, and so PCA fails because PCA was unsupervised. It captures the direction of the greatest variance, and there's no notion of a task. And sometimes the direction of the greatest variance can be noise. And so it's catastrophic for preserving the class info in some cases, whereas CCA has external supervision. And so the two views track one another the way we do it. And in the process, it can actually sometimes suppress noise, okay? So, and it looks like, okay. I will skip. So here's a very nice example, right? Of how this can be done, where this can be used, and how this can be used for a third downstream task. So let's say you're performing speech recognition. What is speech? How is speech generated? I speak. When I speak, I'm moving all of my articulators, my tongue, my mouth, my throat, and so on. And so the speech signal is actually reflecting the movement of all of my articulators. This causes a movement of air. You get a pressure wave. And when you record the speech signal, you're actually measuring this pressure wave. But this pressure wave is not entirely controlled by the movement of my articulators. There are external influences. There is air in the room, air is moving around. There are other things going on, which have absolutely nothing to do with what I say, right? So if I really wanted to record speech, what is the best thing for me to be doing? Yeah.
The actual movements.
I can actually stick electrodes all over my mouth, inside my mouth, have a whole bunch of wires, and record the actual movements of my articulators. And those would be the best way to actually recognize speech, right? How many of you want to walk around life with wires hanging out of your mouth? Nobody. So what can I do? I can say the articulatory movements do not have this noise, but then, they're hard to get. They have other kinds of noise, There's some movements of your articulators that have nothing to do with speech. And so here's what these guys actually did in a very nice experiment. They got a small collection of data where they had people speak and stuck a bunch of articulators into their mouth. And then they used canonical correlation analysis to derive basis representations of the speech signal that track the articulator movements as measured by the sensors. And now, of course, for the rest of it, you can just use those bases to characterize all subsequent speech and use those to recognize speech. And you find that it's considerably better than anything you can do, which doesn't actually explicitly target articulator movement. So you get an idea of, how you can actually use these in different settings, right? So can somebody answer this first question? True or false? Second one? False, right? So it's supervised, and you use the supervision to reduce the noise in the data. Everybody with me so far? Okay. I have 6 minutes, so I'm going to rush through the next topic, right? Now, in what we did so far, we were performing regression. Y was a continuous valued variable, and we were trying to predict Y. What if Y is a discrete variable? If I'm trying to perform classification, it turns out CCA can be applied. So if I think of Y as a discrete variable, but then I use a one-hot representation for Y, then you can just use CCA, and you get what is called linear discriminant analysis. But often LDA is presented from a different perspective. So here, let's say I have these two data from these two classes, the red and the blue, and it's in 2 dimensions. Now, if I want to project the data down to 1 dimension, if I use PCA, which dimension is it going to project it onto, the blue line or the red line? Over there. In this case, where will PCA actually project the data? Out here. Where would principal component analysis project it? Why the blue line? The direction of the maximum variance, right? Which direction has the maximum variance? The blue, right? Is that useful for distinguishing the 2 classes? Not at all, right? Similarly, if I were doing a principal component analysis of this guy, there's really no way of knowing which direction it's going to be projecting things into, although there are 3 classes, right? So in LDA, you say that, okay, here's this additional information about classes. And the class is the second view. And now I can try to find projections where the projection predicts the class best. And it turns out that LDA and CCA are the same thing if I use one-hot representations for my classes. But then there's a different way that people come up with. So here, let's say I have my 2 data, my data for my 2 classes, and you keep searching through space to find the hyperplane or the line such that when you project data onto that hyperplane, the separation between the classes is maximized. So here, if I project all of these data onto this line, here is the histogram for the 2 classes, and you can see that the 2 histograms overlap, right? Whereas if I project them onto this line, you can see that the histograms, once I project it, the location of all the blue points is very distinctly separate from the location of the red point. So the 2 histograms separate out nicely, right? And so if I'm going to be projecting things down to just one line, 1 dimension, which of these 2 would I use if I want to perform classification? First or the second? The second one, right? How do we find the second? And so what we do in LDA is very straightforward. You define something called a within class scatter. So again, since I have 3 minutes, let me go through this really quickly. You have, well, let's say I have data from one class, data from another class, and data from the 3rd class, right? So the within class scatter is the variance of this group. The within class scatter for this group is the variance of this group. The within class scatter of this group is the variance of this group. Okay, so there are n1 instances here, n2 instances here, and n3 instances here. Then I'm going to have n1 times the scatter 1 plus n2 times scatter 2 plus n3 times scatter 3 divided by n1 plus n2 plus n3. And this gives me the average within class scatter, which tells me how compact the classes are. Right? Then I can also look at their three means. And I can look at these three means and think of them as data points. Right? And I can look at the variance of those three guys. And that is what is called a between class scatter. And you want the within class scatter to be small so that the classes are compact. You want the between class scatter to be large so that the classes are far apart. And so the standard arithmetic is that you want to find some projection that minimizes the within class scatter while maximizes the between class scatter simultaneously. I'll skip this, just take a look at the slides. I'm very smart about these things. I don't teach, I just put it in the quiz. So all of this is going to be in the quiz. And which means you're going to have to do the reading yourself and pretend I'm teaching you and you'll answer the questions. Does that work for you guys? Does that work for you? She's looking very unhappy with it. Okay, so there was some, and LDA will fail, will work nicely when the data are non-overlapping and all the classes have roughly the same variance. If the classes have different variances, then it's sort of, you have to do something called heteroscedastic LDA, which I won't even get into. It will not work when the classes are overlapping, like this guy here, right? Because there's no projection that will separate them. And so LDA needs assumptions that the classes are roughly Gaussian and distinguishable as relatively compact clusters. It assumes that the classes have the same variance, but then you can eliminate that assumption using something called heteroscedastic LDA. So here was a very nice example of how they showed that LDA and CCA can actually get you good representations. So what they did was, there's something called the vowel triangle. So when we speak, we generate different vowels, and the vowels come from different parts of your mouth. A comes from here, E comes from here, U comes from closer to the lips, right? So you have front, mid, and back. Then in each of these things, you can say O or U. So it's open or closed. And so depending on the kind of articulation, you have different categorizations. And so you can actually draw a two-dimensional chart. And in this two-dimensional chart, the different vowels end up in different locations. So in this particular experiment, they collected a whole bunch of readings from the tongue. And then they tried to perform CCA on it to see what kind of groupings PCA got. And this is the best way of mapping the two-dimensional PCA projection on the vowel triangle. Each color represents a different vowel. And you can see that PCA doesn't really manage to segregate the vowels at all, right? When they perform canonical correlation analysis, you can see that CCA actually begins to, where they're predicting the articulator positions from speech, you can actually begins to separate the vowels out in the right positions. And in this case, because the phonemes are very distinct, you can use linear discriminant analysis and does a much better job. So again, stop here. I skipped most of the lecture because I spent a lot of time on the fun stuff and skipped the ugly stuff. I'll leave the ugly stuff for the quiz. Any questions? Does that make sense at all? Make sense? It didn't. Look at her face. Thank you.